Let's consider formal charge. This is a method used for covalent substances to assign the charge on the atoms. Now, they don't really have that charge. They're sharing electrons. But by doing so, we can get a good idea of the electron sharing that's going on, and it particularly applies well to substances which have a net charge, or for which when you try to draw them, the electron dot structure fails. Let's look at several examples. Consider ozone. This is O3. It's all over the place in our atmosphere, right? And you might say, oh, I know how to draw that. I'll just draw a triangle. And you know you'd be right, because that would just be every oxygen has two bonds and two lone pairs, and it would be perfect. Oxygen does typically form two bonds. But it's observed when they analyzed it to have a linear structure, right? It has, or I should say, I'd say a slightly bent structure. In any event, it's not a ring structure. How can we draw this thing? It can't be done really, right? You can't put two bonds on each one if it's going to have that structure, and yet it exists. So we have to do the best that we can. Draw it together, make it a little bit off, and then evaluate the charges. We can do that by counting up electrons. If they're a lone pair, they're wholly owned by that oxygen, right? It wants to have 6 valence electrons. 1, 2, 3, 4. If it's a bond, they're shared, right? So this is garden variety oxygen. 2 lone pairs, 2 bonds. I count 6 valence electrons. That's nice, no charge. Maybe not for this one, though. 1, 2, 3, 4, 5. It's missing one. We're going to put a positive charge there. And how about this one? I see 1, 2, 3, 4, 5, 6, and an extra 7. This is called a zwitterion, or an internal salt. And there it is, plus minus right there. You'll find that the bond lengths are the same. That has to do with something called resonance. That's another topic. But that's how we analyze a substance in terms of formal charge. Let's try it for the carbonate dianion. Clearly, we have to come up with a way to draw this so that there's extra electrons around. How should we do that? Well, I'd put carbon in the center. I'd put each oxygen around the end. I'd start with single bonds, and then I'd double up where I have to. Let's double up right here. And now let's evaluate it. Do we have our charges right? I see 7 electrons here. Remember, count the bonding electrons as 1 each because they're shared. That's negative charge. 7, it's supposed to have 6. 7, it's supposed to have 6. 6, it's supposed to have 6. 4, it's supposed to have 4. Do you see that? This is one form of the carbonate dianion, a pretty reasonable one. Right? When you're drawing these, you might come up with a structure that has a negative charge on carbon, but that's not reasonable. Oxygen is far more electronegative. It's the one that would naturally assume the negative charge. And there's the analysis that we went over right there. Looks good to me. Try the hydroxide anion. Draw it as a Lewis structure. Oxygen wants to have 2 bonds. We're going to have to draw it a little bit differently, right? We'd have to have a negative charge somewhere. I'd put it on oxygen. Hopefully, you could pause it and try it. I hope you came up with this. This oxygen has 7 valence electrons, hence the negative charge. This hydrogen has 1 valence electron that it's sharing, hence no charge. That's the hydroxide anion. Okay, nitrate. If you can do this one, then consider yourself a formal charge expert. I hope you drew that. Let's evaluate the charges. I think something's missing here. I like 7, so the minus charge there. I like 2, 4, 6, 7, so the negative charge on oxygen. Remember, it's supposed to have 6. Should we put a charge on that oxygen? 1, 2, 3, 4, 5, 6. No, it's perfect. Should we put a charge on that nitrogen? 1, 2, 3, 4. If you said yes, that means you're really getting this. It's supposed to have 5. We need a positive charge there. You know, I think it's a typo. I think I should have a plus charge there. And by the way, as drawn here, can you see that it's NO3 minus? No, it's only supposed to be minus 1. So put a plus charge there, and you got it. Finally, we can do the same thing with the ammonium cation. We have to break a honk rule. We have to give it an extra bond, and you should notice that the positive charge is on the nitrogen. This is formal charge. As the year progresses, once we get into ionic substances, you're going to see that we'll use a different system of bookkeeping, and we call that oxidation number. It's not uncommon for students to get the two confused. I think of it as we just use these for covalent things, count the dots. For the ionic substances, we start using automatically, without really thinking about it, a different system of counting things up, which we call oxidation number. I don't think you have to go to a whole lot of trouble to worry about the difference between one and the other, but if it's bugging you, you can check out this link. It's, I think, a nice evaluation. It takes a little time, but it's a pretty good evaluation comparing formal charge and oxidation number. And this is an introduction to formal charge.